what I've been doing thus far, like when we do cosmology as a theorist, we are computing usually the 3D Fourier space power spectrum, right? So of the total matter Fourier space power spectrum. We cannot measure this because we can't measure anything in 3D, and we can't measure matter, right? We're sensitive to some tracer. So in reality, the galaxy surveys will measure the 2D angular power spectrum of galaxies, and that traces the 3D matter power spectrum. The Lyman alpha forest will measure the 1D redshift-based power spectrum along the quasar sight line of neutral. So the 1D redshift-based power spectrum of neutral hydrogen along the quasar sight line, or the 3D redshift-based power spectrum between quasar sight lines. So there are two Lyman alpha forest statistics that people look at. One is you have a quasar sight line, you're observing it here, the sight line is kind of over there, and you transform along the line of sight, right? The other one is you have one sight line here, one sight line over there, and you correlate absorption between the two sight lines, okay? All the BAO are done with this one. All the small-scale cosmology are done with this one, right? So I'm going to talk about the 1D redshift-based power spectrum mostly. People who are interested in BAO will use the 3D redshift space power spectrum, okay? There are, of course, strong projection effects when you move from this to any of these, right? And dealing with the projection effects is part of what we have to do as cosmologists. So this is the only slide I have on the 3D redshift space power spectrum. I felt that I should talk about it because, the BAO are kind of important, right? But this is the only slide I have. So this is how it works. This is the linear theory power spectrum. This is the 3D power spectrum. It's measured in terms of K, or scale, and mu, which is the angle between the two quasar sight lines. So mu of 1 is 0 angle and along the line of sight, and mu of 0 is your one sight line is over here and one sight line is over here, right? So this is the cosine of theta. So mu of 0 is theta of pi by 2. The form that this has is a linear biased form. It's amazing. Like on large scales, everything is a linear bias tracer of total matter power spectrum. So there's a linear bias. There is also a velocity bias, because as I've told you, the Lyman alpha forest is intrinsically a velocity space measurement. So you have this velocity space measurement, b eta, times by this angle squared. And then we also have this nonlinear correction term. So this is just to say that on large enough scales, you can measure a 3D redshift-based power spectrum, and it works kind of like the galaxy power spectrum. You still have a linear bias term. You have stronger redshift space distortions, but the intuition that you expect from galaxies is kind of still there, okay? Now let's talk about the cool stuff, which is the 1D flux power spectrum. So here is a sight line. What we're going to do here is we're going to work out the correlations of absorption along this sight line, right? So this is if I have an absorber here, what is the chance that there is another absorber 10 megaparsecs away, right? This is the Fourier transform of the 1D correlation function along the line of sight. The way we work it out is that we first compute the flux excess. So this is the mean flux along the sight line. Sorry, no, this is the mean flux in the box along all sight lines. This is the flux along the sight line as a function of velocity, and we make it dimensionless. We then take the power spectrum along the line of sight, the 1D Fourier transform, and we correlate it to take the power spectrum. And then we average over many sight lines, right? So we have a box with a whole bunch of sight lines in. We take the Fourier transform along each one, and then we average over them. What are we doing here? Implicitly, we are integrating out two angular directions, right? So this is how we go from a 3D power spectrum to a 1D power spectrum. We are integrating out x and y and keeping z, okay? This is, so as cosmologists, you have intuition about how the power spectrum behaves. And one intuition that you have is that the power spectrum has independently distributed Gaussian error modes, right? That you measure k at 0.01 and k at 0.012, and they are independent of each other, right? This is not true for the 1D power spectrum because you have integrated over X and Y. And that has mixed long wavelength modes in the X direction and short wavelength modes in the X direction, right? So everything is horrifyingly correlated in this 1D flux power spectrum, okay? So all the intuition that you have, that you think, the way that you think a matter power spectrum should behave, this is not the way that the laminar forest behaves because you have done this integration to go from 3D to 1D, all right? Like, it's strange of me, it's strange to, people don't say this, and it's strange to say this because you don't, the way that you expect a 3D power spectrum to behave is kind of weird, right? Like most things do not behave in this way, right? You do not generally separate modes. You do not generally get to say, oh yeah, this mode is separate from this mode. The error bars are diagonal, everything's great. That's an unusual thing to do, right? So most people who are not cosmologists do not have this intuition, right? I'm only mentioning this because this is a cosmology summer school, and probably everyone knows this at some level. And so if you then try and do laminar forest analysis, you're going to be tripped up, okay? So don't get tripped up. Unlearn the thing that you think you know. Yeah, so this is the 1D flux power spectrum. This is a measurement at redshift 2.6 from different data sets. The units, of course, are seconds per kilometer. This is, you can, it is true that if you make matter more clustered and thus increase the amplitude of the matter power spectrum, you will also make the neutral hydrogen more clustered and thus increase the amplitude of the flux power spectrum. However, the exact relationship between this and the matter power spectrum that you put in is somewhat complicated, right? It does not behave nicely in the way that you think it should. And also the way that it evolves with redshift between redshift 4 and redshift 2.6 is very important, right? So there are, if you just had this one redshift bin, there will be strong degeneracies between the astrophysical parameters that I'm about to talk about and the cosmology, right? The only way to break these degeneracies is to look at the redshift evolution between like redshift 2.6-ish and redshift 4. Okay, that's the thing that actually gives you the cosmological constraining power, right? Okay. Yeah, okay, okay, so I'm told that many people actually cannot, that too many people were trying to download my Google Drive file, and so people did not actually get to plot the spectrum. So I'm sorry, I don't control Google, but every time you do something, a demo like this, it always goes wrong in some way, so what can I do? But you can, this gist is available so you can plot it later, I guess. So okay, so let me show you some sightlines. Let's plot some sightlines. So these are 32,000. I said you need to average over a bunch of sightlines at different angular positions. 32,000 is about the minimum that you need to get a reasonable, to beat down sample variance enough to get a reasonable power spectrum. When I'm doing this for real, I use about 1 million sightlines per box, right? So more sightlines are better. I'm going to plot the 100th sightline. Why not? And it looks like that, right? So this is a simulated Lyman alpha forest, right? This is not selected to have a DLA in, not selected to have a galaxy inside it, so it doesn't. There's a ton of different lines, right? So you can kind of see this, like, by eye, this looks like a mess, right? Like, by eye, like, what is the cosmological information here, right? But you can see that larger absorbers have kind of a characteristic separation of like maybe 1 to 2,000 kilometers per second. Smaller absorbers have a smaller separation. Yeah, let me do the next exercise a little later. This kind of looks like a mess, but it looks like a mess with different lines in, right? Like this kind of looks like a frequency plot. It looks like, oh yeah, let's put this into frequency space. Seems like kind of a natural thing to do. Okay, that's what I want you to get from this plot. I can also plot a different sight line, which will be at a different position, and it looks different, right? But again, the lines are separated at some characteristic scale, which makes you think that the power spectrum is the right thing to look at. Okay, let's go back. Okay, so actually, no, let me this might not work. So okay, let's overplot two spectra. Nope, that's not. Okay. Let's overplot two spectra. Yes, okay, let's overplot two spectra. So here I have the two spectra I just plotted on the same plot, and I've just pulled out a chunk of the spectrum, just a small chunk, just to show you. And you can see that the lines are in different places, right? But the lines are separated by kind of constant amounts, like this guy and this guy and this one and this one. So again, it looks like frequency space is kind of the place to go, right? So we go into Fourier space. So this is what we do. This is how we compute the flux power spectrum. This is the same thing that I put on the slide. This is the code that works out the flux power spectrum. I work out the overdensity. This is the flux here, the exponent of the optical depth. This is the mean. So this is a delta, a dimensionless delta. I work out the power spectrum for every single spectrum in turn, and then I average them, which is this, and I make sure I convert the units properly. And I get something that looks like this. Yes, I do. I get something that looks like that. Hey, wait a minute. That doesn't look very much like this. Why doesn't it look very much like this? Well, it's because I'm plotting it in the wrong units. Let's do this better. Kf times this by mp dot pi. Ta-da! Okay, so now this thing kind of looks a bit like that, right? Let's put this here. This one looks like this. So, okay, k of 0.01, it's kind of big. K of 0.01, round about here, it looks kind of big. 0.05, 0.05. This looks kind of plausible, okay? This is, of course, in log space. I could even make it into linear space. Nope. Semi-log x. Yeah, there we go. Okay. 0.001, 0.02. Yeah, close enough. It looks kind of right. Okay. I think maybe. Yeah, there we go. Close enough. It looks kind of right. This one looks kind of like that. Okay. So what I want you to get from this is that yes, I'm not just making stuff up, right? Like yes, I have this complicated simulation pipeline, but if I look at the flux power spectrum that comes, the predicted observable that comes out of my simulation pipeline, it does look kind of like what a real universe looks like, right? This is an important cross-check for any simulation pipeline. And if I had not done it, you should not believe me, okay? And this was a thing I learned like in second year of grad school when I was working on something and it didn't really work. And my advisor said, have you tried plotting the data? And I said, no. And he said, why don't you go do that? And I did. And the problem was apparent immediately, right? It was obvious. I had missed like a factor of 2 pi or something because all my data was like 2 pi below what the observer was with. I multiply by 2 pi, everything starts working, okay? So that is the moral of the story. I've only got 25 minutes. I need to hurry up. Okay, so we want to get some cosmological parameters, right? So the basic trick here is that we have some linear theory matter power spectrum like this. We know how to plug it into a simulation, run a big simulation, blah, 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 sits on a supercomputer, and out pops this simulated flux power spectrum that we just saw in the GitHub GIST, in the Colab GIST. This doesn't solve our problem because it tells us whether our simulation is in agreement with the observations, but it doesn't tell us how, what the best cosmological parameters are, right? It doesn't tell us the uncertainty on the cosmological parameters. To get that, we need to invert this. We need to say, okay, we have this observed flux power spectrum. How does that go back to the matter power spectrum? We can't do that with a simulation. The way we do that is we build a surrogate model with some kind of machine learning approach. In practice, we use a Gaussian process. I'm not going to talk about that. You can ask Mingfeng about that afterwards, after I go home. Or you can read my paper, or you can read our papers. Broadly speaking, what you do is you run a bunch of simulations at different cosmologies. They are able to predict a flux power spectrum. You build an interpolator that is able to predict what the flux power spectrum would look like for an arbitrary set of cosmologies, and then you use that to run a Markov chain, just like you normally would. Okay, so that's what we're doing here. So this is kind of saying that there's a whole bunch of machinery under the hood that I'm not going to talk about. Okay? There are also some nuisance parameters. So this is like the astrophysics of this problem, right? So I told you that the ionization fraction of the universe was about 10 to the minus, the neutral fraction of the universe was about 10 to the minus 6. This is the mean ionization fraction of the universe. This is controlled by the number density of ultraviolet ionizing photons. To demonstrate this, so remember the optical depth is this integral of the neutral hydrogen density times by some cross-section along the line of sight. So we're sensitive to the neutral fraction. This neutral fraction is set by an ionization equilibrium balance, right? So we have in the universe an atom of hydrogen. It will be constantly being ionized by UV photons, by the UV background, and going to a proton and a dissociated free electron. That free electron will then be constantly recombining with the free proton, boom, to get neutral hydrogen again, and then emit another ionizing photon, or a Lyman alpha photon, okay? The balance between these processes, because these processes are fast with compared to the other processes, you get an ionization equilibrium balance, and the ionization rate balances the recombination rate. What sets the photoionization rate? The photoionization rate is set by this factor J, which is the number density of UV photons, right? So what this is saying here is that the neutral fraction of the universe, the number density of neutral hydrogen, is set linearly, almost, by the number density of ionizing UV photons. So this is fine, of course, because we know the number density of ionizing photons, right? Right? No, we do not know the number density of ionizing photons. We have no idea what the UV background is in the universe. It's canonically very difficult to measure, right? So of course you know where galaxies are most of the time, but you don't know what their UV emissivity is. You don't know what their UV escape fraction is. So actually the best way to measure the UV intensity in the universe is through the Lyman alpha forest, actually. So this doesn't help us, right? So what we'd like to do is to set a prior on this. We can't do that. So what we need to do is to marginalize out the mean optical depth, tau, and through that get a handle on the UV intensity. Conceptually, this is similar to a linear bias argument for galaxies, right? So this is setting the number density of neutral hydrogen, which is also the ratio between the observable, the flux power spectrum, and the matter power spectrum. So just as the linear bias of galaxies sets the ratio between the galaxy power spectrum and the matter power spectrum, so this mean flux parameter, the mean optical depth parameter, sets the relationship between the flux power spectrum and the matter power spectrum, right? And that's why you cannot just look at this flux power spectrum and read off a sigma 8, right? Because you might want to say, okay, hey, I'm going to measure the amplitude of this flux power spectrum. After all, it's roughly flat at redshift 2.6, and I'm going to read off sigma 8. You can't do that because the amplitude of this flux power spectrum is set by the bias parameter, which is the mean optical depth, right? Instead, you're forced to use multiple redshift bins, marginalize out over the optical depth, and when you're done with that, what is left gives you the mean clustering, okay? Exactly as you do for galaxy surveys. The big advantage of the forest is that we know this relationship between the optical depth and the unknown physics, and we know that it's linear to smaller scales than we know for galaxy bias, so we can probe smaller scales without having to worry about it, okay? Any questions on this? Good, okay, yeah. The other thing you have to care about is the gas temperature, right? So the gas is tracing the dark matter, except that the gas has some thermal broadening, right? The gas is moving with respect to the dark matter because of its temperature. So I wrote down this equation for the optical depth. This was a simplification. The real equation looks like this. It has some atomic physics. So this is some line transition. This is the neutral hydrogen density. This is the broadening function due to the atomic physics in the line. So it has two, this is the Voigt profile. It has two components. One is the natural broadening. This comes from the quantum uncertainty in the atomic energy of the transition. It is usually subdominant. The other one is the Doppler broadening, which is the spread in the velocity of the atom due to the temperature, right? So this is kind of like a peculiar velocity for an atom, right? We have a cloud of gas. Within the cloud of gas, particles are zipping around at some random thermal velocity given by the gas temperature, okay? This is the most important one. Fortunately, it's a Gaussian, so it drops off, but it is most important. So this sets the minimum scale accessible from the forest. It's not an instrumental limit. It is a physical limit, because on smaller scales, the thermal broadening of the gas dominates, right? So this K of 20 that I said, this is because this is the limit at which the line is thermally broadened, right? This is this B parameter. This is the width of the line. This is how small you can go without everything becoming hopelessly confused by thermal motions, all right? So you need to know the gas temperature, right? If the gas is at 50,000 Kelvin, the thermal broadening is going to be different than if it's at 5,000 Kelvin, okay? So you might say, wait a minute, why is this, like, wait a minute. Why does this matter, right? Why do we know what the gas temperature is? You have a simulation. Like, the whole point of this is that you can simulate neutral hydrogen. You just spent like 10 minutes telling me that neutral hydrogen is relatively easy to simulate. So why is the thermal history, why is the temperature of the gas a parameter that adds uncertainty to Lyman alpha cosmology, right? Anyone want to guess? Okay, so yes, we do know how hydrogen cools, right? We're good at that. What we do not know is reionization, right? So we do not know how reionization heats the gas. Specifically, the hydrogen reionization completes before we start looking at the forest. So it sets the initial gas temperature at the highest redshift of the forest. The thing that we don't know about is helium reionization, which is where first ionized helium goes to doubly ionized helium. This causes the gas temperature to shoot up at about this redshift and then drop once it's finished and everything cools. So understanding this process of helium reionization is what allows us to set the gas temperature and is the thing that we have to marginalize over. Okay, so this is like the astrophysical uncertainty in the forest. It's kind of, no one else cares about helium reionization, right? You will not find a lot of papers about helium reionization. It is only important for the forest. So this is kind of irritating because you have to, if you're working in the Lyman alpha forest, you have to do work, right? Like normally you want to just take the model that someone else wrote for some other purpose and just shove it into your cosmology and not worry about it. Because helium reionization is only really important for this, you cannot do that. So we had to develop our own model. This is our model. Each of these stars is a little quasar, and we place the quasar in a position, and it ionizes a 30 megaparsec bubble, and it's a wonderful model, and you can read the paper, and I don't have much time. Let me skip that. Yeah, let me do this. Okay, so those are the nuisance parameters. Okay, so the Lyman alpha forest is sensitive to two nuisance parameters, the mean flux and the gas temperature. We're also interested in knowing what cosmologies it's sensitive to. So I told you that it traces the dark matter. We could treat this as a whole sort of set of modes. We want to simplify further. I told you that all the modes are correlated. Because they're all correlated, we treat this as a single amplitude and slope of the power spectrum at a particular scale and at a particular redshift, right? So that was the thing that was plotted on the first slide that I showed you with the matter power spectrum on small scales. It is the amplitude of the matter power spectrum at K of 1 inverse megaparsec at redshift 3. Note that the redshift is not important. The redshift is not important because redshift 3 is during matter domination, and we believe we understand how structure grows during matter domination, right? So we don't have to worry. We can translate redshift 3 measurements to redshift 2 measurements to redshift 100 measurements, freely, because we don't have to worry about what dark energy is doing. It's just matter domination, okay? So we defined these two summary statistics from the Lyman alpha forest. delta L, which is the amplitude of the power spectrum on k of 1 inverse megaparsec, and NF, which is the slope of the power spectrum at k of 1 inverse megaparsec. To connect this to neutrinos, so neutrinos will reduce the amplitude of structure on small scales. They will reduce delta L, right? So a neutrino mass is going to show up as delta L lower than the predicted value from Planck, okay? Notice that we have to be just a little bit careful, right? So because we are comparing two experiments, a systematic in either one is going to mess with us. So if we have understood Lyman alpha correctly, and if we have understood the CMB correctly, and if we have understood how structure formation works correctly, then we can compare the amplitude of the matter power spectrum from Lyman alpha to the amplitude of the matter power spectrum from the CMB, and we can get a neutrino mass limit, okay? Assuming that dark matter is CDM, right? So if dark matter is not CDM and structural formation proceeds in a weird way, then again, we have to rethink ourselves, okay? So this is a measurement that can be done, but you have to be quite careful. Okay? An example of how careful you have to be, there's the previous, some previous constraints on neutrino mass from the Lyman alpha forest, which were quite tight, said that the neutrino mass was less than about 0.1 eV. I believe it is now kind of agreed that these are not valid constraints, right? These were overly tight. They were driven by a discrepancy between power on CMB scales and power on Lyman alpha scales. So what was happening was the Lyman alpha power was measured as higher than the power on the CMB, right? And that just led there to be not enough room for the neutrinos to suppress the power. That made the constraints very tight, but I think is not real. We believe, based on something that I found and now confirmed by the EBOS group, that this comes from an insufficiently accurate theory analysis and also from a data issue in the low redshift bins. I'm going to, there's a reason I've been showing redshift 2.6 data is because the issue affects the redshift 2.2 and 2.4 data. And I'm going to skip ahead to the punchline, I think. Yeah, let me skip ahead to this punchline. No, actually, what time is it? Yeah, okay, let me skip ahead to this punchline. Okay, so let me say this a little bit. Okay, so we did an analysis of the Lyman alpha forest, a new analysis using the Priya simulations. They are named after my wife. This is a good choice. These are 50 very large simulations with 1,500 cube particles and 3 exceptionally large simulations with 3,000 cubes particles. They look like this. So this is Ming-Feng's movie. I don't have, like I said, I don't have a Hollywood movie today. This is the next best thing, going straight through the box. These are full hydro simulations. The way we've been able to get away with doing 50 illustrious-like simulations is that we stop at redshift 2, right? The redshift 2 is a long time ago, so it takes much less time to evolve to redshift 2 and then stop than it takes to go all the way to redshift 0. Okay, so that was the trick that we used. As Tom said, everything Tom said about lattice simulations and how you have to make sure your boxes are converged, that is double for cosmological simulations, right? You really need to make sure these are converged. The issue is that usually you're running a simulation that is as large as you can, that is as large as the machine, as the supercomputer will take. We ran these using the 9th largest supercomputer in the world. There was no way we were going to do a bigger simulation. So we had to, you have to get a little bit creative about your convergence sometimes, okay? And in this case, we got creative by running a slightly different simulation rather than a bigger simulation. I want to say this. This code is public. If you want to download it and run it on your Linux laptop, you can totally do that. If you are running, sometimes there are a group of people that run dark matter simulations and kind of are scared of Hydro. Don't be scared of Hydro. Download MP-Gadget or any other gadget and run a Hydro simulation. It's not as difficult as it sounds, I promise, okay? It's a lot easier than it used to be. We generate spectra from it. And we do our analysis. And I when I'm doing this analysis, I am hoping that all the problems go away, right? I'm hoping that I do my analysis and I get something that agrees perfectly with Planck, and maybe like has some tentative detection of neutrino mass at like 0.01 eV, 0.05 EV, and it's at 1 sigma, and I can say, hey, look, tentative detection, give me more money, then maybe I'll have like a Nobel Prize later. This is my hope, right? This does not happen, right? So what happens is I do my analysis and I get this little yellow blob. And the little yellow blob has a slope which is comparable to the Planck slope and should be 0.97 of 0.9. And it has an amplitude that is way, way off Planck. And so like I have this chain that I run, and it's just like, it's awful. It disagrees completely with the CMB. So I am devastated because what's going on here? And then I tell my grad student, pictured here, why don't you go and plot the data? Aha, so this is what he does. So here we have the plotted simulated data in the solid lines and the observed data in these dots. And you can see the agreement is not that bad, except in the lowest redshift bins, the agreement is kind of terrible, right? So I'm like, oh, that's kind of interesting. This dotted yellow line is really not very close to this solid black line, right? That's kind of weird. Oh, hey, what happens if you just throw out these two bins that don't really match? Well, then you get this red curve, and suddenly the slope of the power spectrum is exactly what Planck wants it to be. And the amplitude is much, much closer to what Planck wants it to be. And I'm like, haha, this is great. And then I have like, I have a moment of doubt, actually 6 months of doubt, because you're not supposed to do this, right? You shouldn't analyze data and then throw the bits away that give you the wrong answer, right? Like that's not a good thing to do, right? So I'm sitting here, having 6 months of angst. Should I publish this? Because this is an a posteriori data selection thing. I shouldn't do that. And then I am saved because the DESI collaboration publishes their 1D flux power spectrum, and their 1D flux power spectrum does not agree with the EBOS 1D flux power spectrum in exactly these two redshift bins, right? So redshift 2.2 and 2.4, they are off by a couple of sigma. And I'm like, okay, something's going on here, right? If there are two surveys measuring the same thing and they measure it different, one of them is wrong, right? So I am going to publish this because maybe my simulation is wrong, maybe it's right. Maybe there was some kind of systematic in DESI and it'll turn out the EBOS was right all along and that something's wrong with my simulation. It doesn't matter. I can claim that there is a reasonable probability of a data systematic somewhere. It's not a posteriori anymore, right? So I throw this data away and I do the analysis and it works so much better, and I can do this without a feeling of guilt because I'm told to do it by the data, right? And a priori, I didn't expect to do this. And the reason I didn't expect to do this is that everything is harder at high redshift, right? So if something is wrong with data, you expect it to be high redshift data that is wrong. But when I think about it, I'm like, no, this is the forest, right? So low redshift, everything is kind of to the blue end, right? That's the region where the atmosphere is kind of blocking all the light. The spectra are shorter, like the instrumental noise is harder. And I think about it, I'm like, actually, I can justify this. All the things that can go wrong will go wrong at low redshift. The universe is kind of cleaner at high redshift because there's not that much going on. Yes, the quasars are fainter, but the forest is the same brightness, okay? So I justify it to myself. And these are the answers that I get. I get a slope of 0.98, which compares to Planck's 0.97. And I get a sigma rate of 0.7, which is much lower than Planck's 0.8. But it is extremely close to the dark energy survey's 0.713. So at this point, I'm like, yeah, this is great. I can go for it. I'm agreeing with not one, but two surveys. And the two surveys disagree with each other. So I am in better agreement with both of them than either of them are with each other. No way, I can do this. Okay, so this makes me happy, okay? I want to show this plot. This plot is this reduced likelihood, this amplitude of the structure at K of 1 and the slope. This is my preferred measurement, this red blob here. This is what the last measurement looked like, and this is what Planck looks like, right? So You can see that I am doing better than the older analysis. The slope now completely agrees with Planck. The amplitude is somewhat lower, but agrees with dark energy survey. My error bars are larger because this earlier analysis did not account for helium ionization, right? So that is why helium ionization opens up a degeneracy here that makes this error bar larger, okay? Yeah. It's the temperature. I put a prior on the temperature evolution from a measurement of the an independent measurement of the gas temperature, basically. So if you, I kind of skipped over this because it's overly inside baseball. This gray bar here, this is an independent measurement of the gas temperature, and I have priored my simulations in the blue and yellow lines to match it. Yeah, and you can see that it shifts the posterior contours by like around 1/2 to 1 sigma, which is where a prior should shift the posterior contours. If a prior does not shift the posterior contours at all, it's not doing anything, and you should remove it. If it shifts them by 2 sigma, then or 3 sigma, there's some kind of internal discrepancy, right? But 1 sigma is just about right. I think that's fair. Yeah. Yeah, 3 minutes. Okay. Notice that I've spent the last like 2 days telling you that if you measure structure amplitude lower than Planck, that indicates a non-zero neutrino mass, right? So the naive interpretation of this is that the neutrino mass is like 0.4 eV at like 2 sigma. Naively, when I say something is naively, that means it's probably not really true, right? Like it's 2 sigma. 2 sigma things, they come and they go, right? Like if something is detected at 2 sigma, maybe it will go away next time. Maybe this will go away next time. This is kind of too large to really be a real detection, I would say. So, it doesn't agree with CMB lensing. So is this real? I don't know. Maybe we'll shift up by like 1/2 sigma with the next data set. I don't know. The real implication is that this is an S8 tension, right? So you may have heard there's an S8 tension with the weak lensing, where the weak lensing data prefers less power than the CMB. This is the same thing, right? The amplitude of this tension is exactly the same almost as for the weak lensing. People explain the weak lensing tension, or there have been many attempts to explain the weak lensing tension with AGM feedback. That is fairly difficult to do at redshift 0. You have to be quite aggressive with your AGM feedback model. At redshift 2, it is very difficult to do with AGM feedback. Like, as I said, there are just not enough black holes, right? Like, it is really hard to get this out of AGM feedback. So this is kind of interesting because it indicates that if this is real, either, yes, it's a huge neutrino mass, or it's something weird going on with dark matter, okay? So that is, yeah, 1 minute left. That is the promise of the Lyman alpha forest, right? That we keep going at it. Maybe we can say something interesting about dark matter. And I think I will stop there. Yeah, okay, and take questions. Thank you very much for listening.
Like, is it essentially just sort of a preference for some warm dark matter? Is that?
Yeah, probably for like, the model that would fix it is like some fraction of warm dark matter, maybe like a mixed model where there's like 30% warm dark matter and like 70% cold dark matter.
Okay.
And I'm just taking that from papers, like trying to find dark matter explanations for the weak lensing tension, basically.
Do you have a sense of how like massive the warm dark matter would be?
It would have to be reasonably it would have to be reasonably warm and thus not that heavy, because it needs to suppress like fairly large scales. So like, I think like the most worked out model is like a 20% of the dark matter is like an axion with like some fairly low mass. But like, I don't want to be like, I don't have a preference for any of these models, right? What I'm saying here is that models exist that can explain this from dark matter. Whether, I also do not want to make the strong claim that like that this is a real thing, right? It's a 2 sigma, right? Like, hopefully it gets stronger and becomes a 5 sigma or a 4 sigma, and then I'll jump up and down and say, hey, this is dark matter, this is dark matter. Hey, you know, give us all Nobel Prizes. I don't know, but this at the moment I'm not doing that, right? I'm just saying, hey, this is a bit interesting.
Thank you.
Yeah.
Since nobody else raised the hand, you said you were happy, you agree, you get sigma 8 of 0.7, which is a weird value. But then you're happy you agree with Desi. I'm not aware that Desi got 0.7 anywhere.
Des, sorry, I mean Des.
Oh,
Dark energy
Des.
survey. Yeah, not Desi.
I'm not sure anyone gets 0.7 anymore. It's all 0.8 now.
Are you sure?
Well, depends what the second digit is after 7, but not 0.70.
I think it was like 0.72 or 73 or something at the time when I published the paper.
Okay, I don't remember the second digit.
776 now? The year 3 results.
It's closer to 0.8, yeah.
So at the time when I wrote the paper, I was trying to agree with the year 1 results, right? And they were a little bit more. So, you know, maybe we'll go away, right? I mean, there is now a Desi power spectrum, and if I analyze that and I get like 0.95 and agree with Des again, then that's even better, right?
Desi full shape is 0.83. I just checked because I thought you were saying Desi, but sorry,
yeah. The Desi is 0.83. That's right. But Des, I think, is lower still. Yeah.
Yep. Thanks.
Cool. That's it? Great.